Hello, my name is Daniel Skoog and I'm a product manager for Maple. In this webinar, I will be talking about some of the ways that you can benefit from adding Maple into the classroom to teach statistics. My goal with the webinar is to walk you through MapleSoft's offering for statistics education, starting with the classroom and beyond. Throughout the webinar, I will be showing interactive applications, mostly taken from our collection of math apps, as well as some live math examples from topics covered in basic statistics courses. I'll close today by rounding off MapleSoft's offering by talking about how several universities are currently using MapleTA for testing and assessment in introductory statistics courses. Here are some of the benefits to using Maple in the classroom. In Maple, students interact directly with expressions using standard textbook notation. And this means that students can focus more on learning concepts rather than learning how to write their own functions in complex code. And this is in contrast to some other products that may force students to learn a more complex programming language to get started. Whereas in Maple, students really just start by harmonizing what they see in the textbook with what they see on their screens. So on the left or on the right side here, you'll see an example of some of Maple's two-dimensional math input. And this also makes Maple's interface very easy to use. With things like clickable statistics, it's possible for students to apply common operations to expressions with a click of the mouse. And just with a simple right click, you can, for example, generate PDFs, CDFs. You can sample and visualize data, as well as generating probability distributions, all with ease. And not only that, it's very important that the tool grows with you. As you learn it, you should also have a tool that's flexible and adaptable enough that you can use it in advanced studies. So clickable math, natural math notation, they both make it very easy to use Maple. Maple's robust programming language makes sure that you have all the tools that you need for more advanced studies. And this is actually something that we find is that people learn how to program in Maple and then use that in industry when they go on and they're working. And that's why many of our partners in industry are using Maple as an end tool. And certainly another benefit for education is the fact that Maple is also a tool for technical documentation. So rather than needing to export your computed results to, say, a word processor, Maple features a complete technical documentation workflow. And this starts from importing your data files, to analyzing them, to a fully publishable document. And Maple will just take care of all this for you. And this also includes being able to export directly to HTML, to LaTeX, to PDF, or to even ebook formats. And connected with this is, of course, the ability to work with Excel files. So you can still use all of your data files from Excel directly in Maple. There's really no need to re-enter your data. You can just read them in using our import matrix command. And our last point, and this may certainly be more of an administrative one, but your school may already have Maple. And there's a good opportunity there. Like if you've got a bunch of Maple licenses, why not give Maple a try for that all-in-one math and statistics education solution? But let's talk a little bit more about the statistics package in Maple. And Maple is really unique in offering integrated symbolic functionality for statistics. And using symbolics in statistics education, it offers a more realistic and engaging environment for generating problems, where students can focus more, as we said before, on developing their understanding of the theory. And the students will be, as we said, they're going to be working with expressions that look identical to the textbooks. Maple also has arbitrary precision numerics, and this will often result in more accurate results than you may have seen with other tools. Maple Statistics Package features over 180 commands for descriptive statistics, probability calculations, simulation, estimation, testing, as well as visualization. With Maple, you can also visualize and explore over 35 continuous and discrete distributions, as well as creating an unlimited number of custom distributions by using the symbolic engine to specify your own probability function, or by simply just combining existing distributions. So I think this is probably a good time that I switch over. I'm going to move over to Maple now and do a couple of examples for you. So to begin in Maple, I'd like to start talking about the idea of interactive applications. And in Maple, it's possible for you to generate your own interactive apps. Each one of these will have some type of interface that a student can go in and interact with. It could be through a slider, through a dial, through a plot, any number of different ways. And what we've done inside of Maple is we've designed a number of so-called math apps that walk you through certain key concepts in subjects like probability and statistics. So here you can see a couple of our examples from probability. And here you can, there are lots of different examples here. Here we have an example for coin tosses, or birthday paradox, or the infinite monkey theorem. There are a lot of different examples that we've built such that it can be used as a complement within an introductory probability course. So there's going to be a lot of the commonly found examples. Non-transitive dice is another one that you'll see when you're working through your first course in probability. And the same thing is true for statistics down here, that we've got several math apps that are dedicated just for things like the central limit theorem, or measures of central tendency, or I'll show you this one in a moment, continuous distributions, or even discrete distributions. And as well, at the bottom here, here are a couple of new math apps that have just recently been shared on the Mobius Cloud. And the Mobius Cloud, I'll just open that up for a second just to give you an idea what that is. So the Mobius Cloud is our cloud where we store Maple documents. And what we do throughout our development year here at MapleSoft is we upload any new math apps that we're working on directly to the Mobius Cloud. So that way you can kind of get a sneak preview of some of the content that we're planning on including in our next release. So you can see we've got new math apps for walking through a couple different distributions. There's binomial, exponential, and Poisson distributions here. There's also a math app for working with measures of spread, for explaining box plots and histograms, and a couple more. And I'll show you a few more of these today. And one of the things we'll talk about a little bit more later on, we'll talk about this during our random variables section, is ways that you can actually use Maple as a tool to author some of this interactive content. But for now, let's move on and start talking a little bit about descriptive statistics. So in this first example, I'd like to quickly cover some of the ways we can interact with commands in descriptive statistics, including finding the measures of central tendency and spread, as well as computing some standard scores. Now I'm going to start this example by loading their student statistics package. And the student statistics package is really designed for the classroom. It features detailed explanations and instructions, interactive demonstrations, visualizations, all of which are really great learning tools for teaching a course involving probability and statistics. So to start off our problem, with descriptive statistics, we're really aiming to capture the main features of a collection of information. So say we have, you were asked to summarize a collection of grades. So here we've got a list of marks taken from an examination where students were scored out of a possible score of 100. We might first start by giving, say, a single value that represents the central tendency of the set of data. So let's do so, and we do an example now using some live math. So we'll actually go over here, we're going to open up our expression palette, and let's grab a sum, and we'll go from 1 to 10. There's 10 elements in this marks list here, and we'll just add up all of the values for marks, and we'll just do this underscore I to give us an array, or we basically are working through values of this marks list. And then we'll divide by n, which in this case is going to be 10. So here we can see that our average, or our mean for this set of data, is going to be 651 over 10. And let's just approximate that. So we'll right-click on it, choose approximate. So we'll see that the average is 65.1. All right, so rather than now going through and computing these, say the median and the mode by hand, I'll show you just how to get both of those by using our context menu. So we'll just right-click here on our list, choose Student Statistics, Quantities, Median, and Value. So our value here for the median is 73. Let's do this one more time to find the mode. So the mode is 75. Now, for a small enough data set, the mode is something we could probably even just find by inspection. But for larger data sets, it becomes a little bit more difficult to pick it out if we're going to do it manually. But here's where another feature of the Student Statistics menu is fairly helpful. So if we choose mode, and instead of choosing value, we choose plot, we'll now get a histogram of our data set. And we can very quickly here pick out the red dashed line as being our mode. So this is the most frequently occurring value in this data set. So that's one way that bringing visualization in will actually help to firm up that concept, the idea of the most frequently occurring number or value. All right, so moving on, let's talk a little bit more about measures of spread now. So I'm just going to move down here a little bit. I'll call marks again just to get our list. So measures of spread can be used to describe the variability in a given sample of data. So I want to now show you a couple of methods for finding and visualizing things like the range and the quartiles and the interquartile range of a collection of data. So let's start by, I'm just going to sort my marks. So I'm going to just right click on the marks here, choose sort ascending order. And sorting is handy because now I can do things like determine the range. And the range is simply just the maximum value minus the minimum value. Since we have this sorted, it's just going to be 82 minus 14. It's just 68. All right, so let's talk instead now about another way to calculate spread, namely by looking at things like the quartiles and then the interquartile range. So the median, when we computed the median before, we just did this using the context menu, but when we were computing the median, what we were looking for was the middle value here. So in this case, we would look for, this is a set of 10 elements, so we'd look right here for the 5.5th element or so. So what we'd actually be doing is taking the arithmetic mean of 72 and 74. So 72 plus 74 divided by 2 is in fact equal to 73. So in the same way that the median splits our data set in half, quartiles split our data set into quarters. So one easy way of doing this by inspection is just by looking at the first half of our data set and looking for the middle value. So this means that our first quartile is equal to 62. In the same way, if we split the top half here into halves, we'll see that for our second half, the third quartile is going to be equal to 75. Which means that our interquartile range, which is the difference between the third and the first quartile, is just going to be 75 minus 62, or 13. Now, of course, we could have found any of these just by right-clicking and choosing the Student Statistics menu, but sometimes it's a little bit better for us pedagogically to walk through a problem and to show kind of the tools and to show the theory that we're doing behind the scenes. But in any case, I'll just show you here a plot for the interquartile range so we can capture things like the first and the third quartiles as well as the interquartile range graphically. And now certainly to close off this section, I wanted to quickly mention one more way of looking at all this. And rather than going through and right-clicking and running the commands I have, we can also just return a data summary of our collection of marks. And when we get this, we'll get the full list here with the mean, the standard deviation, skewness, kurtosis, min, and max. And if we'd like, we can also return this as a plot. So just let me right-click again on marks, choose Student Statistics, Quantities, Data Summary, and Plot. And here's our plot, and here we can see is the mean. Here's the mean minus 1 standard deviation, as well as plus 1 standard deviation, and max and min values. So before we leave descriptive statistics, I want to talk about one more measure. And so say we have our list of marks again, and say we were a student whose mark was 74. We received a grade of 74, and we were wondering how we did in relation to the other grades. And we can scroll up here, and we can see that our mean up here was 65. So this leads us to believe that, okay, we are above the mean, so we're doing okay. But realistically, it doesn't really tell us, say, how many students were had a grade less than us, or how many students had a grade that were higher than us. So if we're looking for that type of statistic, we need to start talking about something called a Z-score. And this is the so-called standard score. And this will measure how far a given observation is from the sample mean in terms of standard deviations. So the formula for calculating the Z-score is just that we take our grades, so 74 minus, and I'm going to use some commands now from the student statistics package, so the mean of marks, and then we'll just divide this by the standard deviation of marks. So what we're doing with this formula is we're subtracting the mean, and then we're dividing by the number of the standard deviation value, and this will give us a value for how many standard deviations we are away from that mean. So let me just approximate this to 5 digits. There we go. So this gives us a positive value of 0.45. So this tells us we're roughly half a standard deviation away from the mean. So let me open up a math app to show you exactly what we're looking at then. So I'll open up the ZScores math app, and here is the structuring of one of these math apps. So we'll start with discussing the main concept between what a Z-score is, as well as how we can find p-values from the standard normal distribution table. And below here we have an interactive demonstration. And in this case, the demonstration is attempting to show us the link between the area underneath the probability density function and values on the cumulative distribution function curves. So here, if we just scroll out, if we want to say we had a z value of 0.5 or 0.45, and let me just adjust my slider, there we go. So here with a value of 0.45, we can see that the probability that we have any grade that's less than 0.45 is actually going to be equal to 67. So 67% of the grades are in fact lower than our grade of 74. We can also read this off directly from this cumulative distribution function plot. So here we can just adjust our value for z, and we can just read off the value on the z-axis. Here we have a value of, we saw it before, 0.67. And if we wanted to use this demonstration to showcase this idea, we can basically just drag the slider back and forth. We can see how the area under this curve corresponds directly with values that we're reading off of the y-axis of this other function here. So I want to show you one more math app before we leave descriptive statistics, and that's one covering measures of spread. So I walked you through a couple different ways of computing these by using formulas and by using the context menu, but here's a math app that also covers measures of spread. So again, we start off with the main concept, and here below we have an interactive demonstration where students can choose their sample size. Here we'll drag it out to size 30, and we'll choose numbers between 1 and 20, and then let's start generating some sample sets. If we just click on this button here, we can regenerate the sample set. Then once we have a sample set we want to work with, we can now show things like the max and min values, and then the connection, of course, with the range, that the max minus the min is equal to the range. As well, we can show the median and the first and third quartiles. And doing it interactively like this, it also gives us kind of a picture into, in fact, if the quartiles are symmetric about the mean. So here we can see it's the first quartile is a little bit closer to the mean than the third quartile. And maybe if we regenerate this, we can see how these two shift around. So here we're even closer to the mean, or pardon me, the median. And as well, if we click here, show interquartile range, we can show the connection between the interquartile range and the third and first quartile. So we can show that, in fact, the interquartile range is just the value of the third quartile minus the first quartile. So again, the idea with these math apps is we're trying to give an interactive view into some concept. So we're giving this interactive sliders, checkboxes, whatever it is, that allow students to come in and just regenerate sample sets and get a little bit more understanding of the underlying statistics. All right, so let's turn the tables a little bit, and let's move on and do an example from probability distributions. And in this example, I'll start by showing some of the ways that we can work with random variables generated from various probability distributions. And in a later example, I'll also show you ways that we can generate a custom random variable distribution. But I want to spend a little bit of time during this example talking about ways that we can use Maple to generate interactive demonstrations for things like random variables and as we saw before, measures of spread. We can basically use it as a tool for app authoring. But let's start by talking about some of the commands we have for working with probability distributions. So Maple has support for 38 standard continuous and discrete distributions. And maybe before I get into my example, maybe I'll just look up our math app for continuous distributions. So I'm just doing a search here. We'll just open this up. And this will provide us with a list of a few of our most common continuous distributions. As well, below we can see that there's, again, this interactive section where we can choose a distribution and visualize it using its PDF and CDF. So here, let me just change this from a code sheet to, we'll go over to the exponential. And then we'll go down and we'll choose the normal. We'll be working more with the normal later on. And we'll try the uniform as well. So you can see are a number of interesting distributions, and as well you have this interactive demonstration where we can do things like adjust the range, change parameter values for the uniform distribution, and so on, and get some type of feedback right away. But let me show you now some examples of actually working with random variables in Maple. So I'm going to start by declaring a new random variable. We're going to call this one x, and we're going to declare x to be a normal random variable taken from distribution with mean 0 and standard deviation 1. I'll just go back and load student statistics such that I have this command available, and there we go. So when Maple generates a random variable, it'll return this underscore r notation, and that just tells you that it's stored it as a random variable. So let's start by sampling this. So let's right-click on this underscore r and choose student statistics, get sample, and return a sample of size, we'll go for 1,000. All right, and now this returns a vector to us. So in order to save on screen real estate, we don't want to show you 1,000 lines of this vector, so we just keep it in summary format. And if you double click on that, you can go in and view values within this matrix. But now that we have our sample, let's start to actually work with our sample and find things like the mean of the sample. And we'll find the standard deviation of the sample. And there's lots more we can do with that right-click menu. If we wanted to, we can return the data summary plot. So there's the data summary plot of our sample. Now if we go back, let's just call our random variable again. So here's x. Let's return the PDF for x. So let's find student statistics, properties, and return the probability density function, and we'll give this at a value of x. So here's our PDF for x. Now previously, when I did the status summary, we can kind of see that it has the shape, this almost bell curve-esque shape of the normal distribution in our sample. But let's see what the true shape of our distribution is by just returning a plot. So I'll just right-click on this expression and generate a 2D plot for our normal distribution. So here we can see now we have the plot of the normal distribution. And let's now actually explore the normal distribution a little bit more. So say if we wanted to take these last few examples I've just been showing and turn this into an interactive demonstration. So here I have the PDF for the standard normal distribution, so mean 0, standard deviation 1. But say we wanted to actually explore how, if we varied the mean and the standard deviation, how this would affect the shape of the normal distribution curve. We can do so by creating our own demonstration or our own exploration. So let's start by generating the PDF of our normal random variable, in this case with symbolic parameters mu and sigma. And once we have this, we can now start to work away and generate an interactive plot with two sliders that let us control values for mu and sigma. So to do so, what we'll do is we'll right-click on our expression and choose Plots, Plot Builder. And I'm going to choose to make an interactive plot with 2 parameters. So our 2 parameters are going to be sigma, and let's make sigma go from 0.5 to, say, 2.4 or something like that. And then we'll make our mean go from -3 to 3. I'm just going to adjust my x-axis here to 6 to 6. And then let's go into the options menu just to further customize this a little bit. I'll just add in a title. I'm going to just customize my y-axis just to show a slightly narrower focus. We can also specify the size of our demonstration, so I'll just make this 600 by 400. All right, and now that we've got these custom settings put in, let's just return our plot. So now we get a plot back, and this says the normal distribution. And here we have sigma and mu. So let's see what happens when we change values for mu. So if we drag mu this way, we can see that the normal distribution curve just moves back and forth. So it just moves laterally along the x-axis. So we don't have any effect there, really. Let's see what happens instead now when we change values for sigma. So we'll take sigma up higher. As we go higher with sigma, we can see here that the curve actually kind of flattens out, that the observations get further and further away from each other. We're almost kind of getting towards a uniform state where we almost have a flat line. And what happens if we go in? Let's go down with a lower value for sigma. So now we can see all the observations are kind of clustering in towards that mean values. We're getting everything pulling in towards the center. So this is kind of a handy way, just by generating this interactive plot, that we can work with interactive with these distributions in order to generate interactive demonstrations. And one other command that's available to you within the student statistics package for exploring random variables is just called explore RV. And I won't show that one today, but it's another interactive explorer. If you run explore RV on any random variable, it'll give you a fully interactive demonstration which lets you vary parameters and return summary statistics for any random variable distribution. But now let's move on, and I want to talk a little bit more before we leave random variables and probability distributions about creating some custom random variables. So in order to do so, I'm going to just hit restart here. And I'm going to load up the statistics package rather than the student statistics package. And the reason I'm doing that is I'm loading the statistics package just to get access to one command there, and that's namely this distribution command. So I'll talk a little bit more about that in a second, but for now, the problem I want to work on is I want to create the half normal distribution. And this is a distribution that occasionally is used for in statistics. And it's basically just the normal distribution cropped at all negative values. So we crop off all the negative values. So we'll start by declaring our normal PDF, just to be here PDF of a normal standard distribution. And then the half normal is going to be this piecewise, where it's going to be equal to 0 for x less than 0, and it's going to be equal to 2 times normal PDF otherwise. So now we get this piecewise here. If you're wondering how I entered the piecewise into Maple, it's just by using the piecewise operator over here in the expression palette. So next, to generate the half normal distribution, we can now use that distribution call. And with the distribution function call, we specify its PDF. So we give it a PDF as we're using unapply here to create a function out of this command up here. So if we specify that, we can actually create our own custom distribution with custom probability function. And now simply to create a new random variable based on this new half normal distribution, we can just call that random variable command again, and that'll return a random variable based on that half normal distribution. I'll just turn this on so you can actually see it returning the _r1. And now if we wanted to simply work with this random variable, we can query it, and we can use commands on it the same way we can for anything else, any other normal distribution or other continuous or non-continuous discrete distribution. So here we can generate a density plot of R, or we can find the mean or variance or the moment generating function of R. As well, we can do all these things by right-clicking and choosing statistics and finding the mean, median, mode, and so on, all directly by using the right-click context menu. So I've just I'm trying to show a little bit of both sides. I'm showing you commands as well as the right-click command option. It's usually, in a lot of cases here, anything that you access through the right-click command menu, it's just a shortcut for the underlying library command that we've typed out here. So mean corresponds to the context menu entry for mean and so on. All right, so in my last example, I want to talk a little bit more about inferential statistics. And in particular, I want to focus on some of the additional tools we have for hypothesis testing. And I want to start by talking about our tools for interactive hypothesis testing. So to begin, I should mention that the statistics package of Maple, it does have around just over 10 commonly used statistics tests. And this includes standard parametric tests as well as non-parametric tests. Now for us as educators, we may already know that the z-test is used to compare the means of two distributions with known variance. But for a student that's just starting off, it can be sometimes tricky to navigate through these available tests. And inside of Maple, we feature a test guide tutor that acts as a resource to help them narrow down their options to an applicable test for their problem. So I'm going to start by doing an example here. So say a company produces metal discs with a mean weight of 120 grams and standard deviation of 30 grams. Suppose that the mean weight of 10 metal discs is 118 grams. Assuming a significance level of p is less than 0.05, is the company correct accepting the null hypothesis that the sample does not have different weights on average than the population of metal discs? All right, so our question here is really we're aiming to answer the null hypothesis if the sample does not have different weights on average than the population. So when we talk about on average, we're looking at the means, average and means. These two things are tied together. And a couple other things we know from the declaration here of the problem. We know the population mean, 120. We know the standard deviation of the population is 30. We know that the sample is of size 10, and the sample mean is 118. So we have a couple pieces of information. So let's now use the test guide tutor in order to try to find an appropriate test. So we'll choose Tools. We'll go to Tutors, Statistics, and Test Guide. All right, now in this case, we know that the question is asking us to test on average if the sample is different than the population. So that means we are testing for the mean. But as you can see here, there's also tests available for the standard deviation, goodness of fit, and independence. But we're testing for mean, so let's click Next here. So now we're presented with two options. Do you want to test the mean of a single sample that is assumed to follow a normal distribution? Or do you want to test the difference between means of two samples that are assumed to follow normal distributions? So in this case, we're testing a single sample against our population, which is assumed to follow a normal distribution. So we'll click Yes for the first question, or for the first option. And is the standard deviation of the sample known? Now, from our question, we can see that we know the standard deviation of the population, but it isn't specified that the standard deviation of the sample is known. But in this case, we can actually make an assumption. We can make an assumption that the standard deviation of the sample is, in fact, the same as the population. So in this case, the standard deviation of the sample is going to be assumed to be 30. So then we can say, is the standard deviation of the sample known? We'll say yes, which means we can use the one sample z-test on this. If we want to get a little bit more clarification on exactly what the z-test is, we can press Help, and this will give us more information about the z-test, requirements, description, as well as a sample example. And we can also just click here and click on One Sample Z-Test in order to run a one sample Z-test on our data. So here I've just copied in our data from our list here. And now we want to test our data against the population mean, which had population mean of 120. And we had the standard deviation of the sample being 30. Let's scroll down here and choose test hypothesis in order to run the z-test. So the null hypothesis in this case, the sample is drawn from a population with mean 120 and known standard deviation of 30, or the alternate hypothesis that the population is the sample drawn from the population with mean not equal to 120 and known standard deviation of 30. So we can scroll down here, we can look at the results of our z-test, and we find here that the results are accepted. So there's no statistical evidence against the null hypothesis. If we press return now, this will return the output from our z-test, and we can move forward. So next I want to show you a couple more hypothesis tests. I want to run these manually. So let's start by loading the statistics package. And I'm going to start now by just showing you an example of a t-test. So here's first our array of values for x. And say we wanted to test this sample for a population mean of 5. Then we can run the one sample t-test of x with value 5. Hit return here, and this will give us our output from this test. So here we can see that there's a true value for the hypothesis, and this indicates that there's no statistical evidence against a null hypothesis. And if we're really only interested in the confidence interval, we could just run the one sample t-test again and specify here explicitly output equals confidence interval in order to just return the confidence interval. And we can do this with any of the other statistics from these tests as well if we just specify those as output. So next we'll do some examples of goodness of fit. And the statistics package provides a couple of different methods for testing goodness of fit. So say we consider the following sample, and this represents the number of sales made on each day of the week at a jewelry store, tallied over one sales week, Monday to Saturday. Now we wish to test the hypothesis that the sales are uniformly distributed throughout the week. And this means that the expected number of sales per day is then given by the number of sales averaged over the week. So here we can compute sales per day as the mean. So here we just do we add up all the values for y, divide by number of days is 6, and we get the value to be 20. So then if we make a new list of values, we'll just make this the uniform sales, so we'll have 20 per day. We can use the chi-square goodness of fit test to test our sample y against this uniform distribution here with confidence level 0.05. So from the results, we can conclude that a uniformly distributed number of sales is in fact a reasonable claim. Now if we wanted to get a little bit more information similar to what we saw up with our z-test up here, we can actually turn on a little bit more information reporting for statistics. So we can set the info level for statistics to be 1, and this means when we run that same test again, we'll receive the same table output where we get the full output for the distribution, computed statistics, p-value, critical value, as well as the resulting the results. So if we continue this example a little bit, next let's consider a data set of times during a day when sales were made. So what we want to do is we want to determine if the sales are uniformly distributed during the day. And here we consider an 8-hour working day where sales are measured between 0 and 8. And this is the number of hours into the day. So I'll just load my data set here. So in this case, the data that we have is continuous, and we're actually testing against a uniform probability distribution. So in this case, let's use the chi-square suitable model test to determine if the uniform distribution closely matches the provided data. So we'll run our test. And here we can see that the sale times are in fact not uniformly distributed throughout the day because we have to reject this test. All right, so again, before we leave inferential statistics, I wanted to take you over and show you another math app. So let's open up our z-test math app. And here we have the main concept for what we're doing when we're running a z-test. Then we have an example. And this example is exactly the same as one I just told you about before. So again, we're asking about the company producing metal discs. But below we have a graphical interpretation of this, where now we can adjust values for the sample mean to see where the critical values are. So if I move this over a little bit, we can basically see that here at 111 for our sample mean, we're actually past a critical value. In the same way, if we go this way, we can drag this slider over and we can see that just over 128, looks like 129. We move past that critical point for z-values. The critical value here of being 2 standard deviations away, or z-value of 2. So this kind of gives us a way of adjusting a slider in order to get some determination on exactly how values for the C statistic are influenced and are shown on a normal distribution curve. And below in this example, we have a gradable example. So, and again, this is our same example here for our company producing metal discs. But what we can do with this gradable example is, well, we can regenerate this question with new values. So I can regenerate this. I'm setting new values here in these containers. And now we're going to ask a student to either accept or reject the null hypothesis that the sample weights are different on average than the population of metal discs. So actually, let's use our interactive demonstration here in order to test this. So the population, it's going to be, population mean is 103. Standard deviation is 10.9. The sample size in this case is 50. And the sample mean is 98. So we'll compute this. And here we can see that we're actually within the critical value bounds. So in this case, we'll be safe in accepting it. So here we can see we accept it, yes, and the p-value for the above example is 0.144. So this gives us a way of working away. We can kind of now visualize, if we were to slide this over again, we could visualize that breakpoint, or at which point the values for z are too extreme, or the sample means for this problem are a little bit too extreme that we would have to reject the null hypothesis. So that draws my examples to a close, and unfortunately in these 3 short examples I've really just started to crack the surface of statistics functionality in Maple. So at this point I'm going to return back over to my PowerPoint. I'm just going to skip ahead here to this next slide. So really when we're working in Maple, there's a lot more statistics functionality that I could show you. I've shown you a lot of basic problems today, taken from it's kind of a basic course in statistics and probability. But Maple also suits the advanced studies as well as data analysis needs very well. And in particular, Maple makes it easy to work with data analysis with a wide variety of data visualizations. Here we can see a couple for things like smoothing, interpolation, and data analysis tools are really, really robust in Maple. And Maple also has built-in functionality for things like curve fitting, for regression analysis, for time series analysis, for finance, as well as tools for robust statistics. So there's a lot included in Maple. And the important part here is that there's no additional toolboxes needed. This all comes inside of a standard Maple install. And now to round out the story for education, I want to briefly spend some time talking about testing and assessment. And MapleSoft really offers a complete solution for all your stats education needs. And this includes online testing and assessment. And what we offer for this is Maple TA. And Maple TA is a web-based system for creating tests and assignments, as well as automatically assessing student responses and performance. So this of course, has a grade book, as well as testing, assignments, everything. So Maple TA supports complex free-form entry of mathematical equations, as well as intelligent evaluation of responses. And this really makes it ideal for any course that requires math or statistics. Our system was designed with math and statistics in mind. And in fact, there are many schools that are using Maple TA as an end solution for testing and assessment. And there are also already several hundred free statistics questions available in our Maple TA cloud that are taken from active courses at universities such as University of Waterloo and University of Guelph, which are using it for introductory probability and statistics courses. And just to give you an idea of one of these courses, here is the course syllabus for the Introduction to Statistics course. And this is a course targeted at first or second year undergraduates. And the questions here are designed to span the topics listed here. And in general, what these allow for is practice, as well as homework and testing. And for each topic, we can see that there's a wide variety of calculation questions, and these can have numeric responses, as well as true, false, and all these aim to test the fundamental concepts. And another important consideration here is that these questions are randomly generated too, or can be randomly generated. So we can basically, there's no end to the amount of questions we can author inside of Maple TA. So as such, I'm going to now jump over to Maple TA and show you some examples from Maple TA in this Introduction to Statistics course. So now I'm logged into my Maple TA system homepage, and here you can see are some of the courses that I am instructing, or I've just borrowed content from more appropriately. So here you can see here is our student statistics root course, as well as the course I just previously mentioned, the introductory statistics course. So if we go into this, we can now see a list of active homework or quizzes that are available. If we click on one of these, we can start to step through and see what some of these problems look like. I'll just zoom in a little bit. So you can see with these questions, here are questions where we can ask for things like the median price, and we ask for this as a decimal value. As well, here there's a question that asks if a value is higher or lower in Canadian dollars. So, you know, there are options here for drop-down menus where we can have custom values. Let's step through. And I think a lot of these problems now deal with probability. But here's another question where we have an observation table, as well as some summary statistics shown. And you can see that this looks exactly like math here. So we have got X bar and so on. And here we are again asked to provide a numeric solution. Here's a question for probabilities. So here we're given the probability of A, probability of B, and asked to find another probability. And again, rounding the question off. Here's a problem with a Venn diagram. So we're asked to find the probability of B given this Venn diagram. Here's more probability. Let me skip over. I'll show you some more from this third quiz. I think this has a couple more for some summary statistics. So here's another decimal question that we can round our responses off. Here's one. So let X be a discrete random variable that follows a binomial distribution with n equal to 15 and probability of success of p equals 0.91. So what is the probability of X is greater than 12? So you can see here there's an example for probability. Here's a list of true-false questions. So if there's some subject matter you want to teach, you can ask the students to answer this question where they're given 5 true-false questions. And there's really a lot more here. So I won't go through much more of this today, but if you'd like to see more of the content for introductory statistics within Maple TA, definitely get in touch with us and we can arrange to have a full demo given to you or your school to show you some of the offerings we have for statistics within Maple TA. But for now, I want to draw this to a close, and I want to draw this to a close by talking a little bit more about some of the other resources that are available to you. And I've mentioned this a couple times already inside of Maple with talking about the Mobius cloud, and I'll just bring that up again just so you see exactly what I was talking about. Here's our Mobius cloud over here on the right side of my Maple instance. And here is our web-facing Mobius cloud. So any math app that has been uploaded to the Mobius cloud inside of Maple is also available through our website, mobius.maplesoft.com. So here you can go and you can view any one of these math apps I've shown you today. So say we can go in and view the Poisson distribution math app. And similar to what you saw in Maple, this would of course have interactive sections. Here's the main concept section where we talk about the probability and CDF functions of the Poisson distribution. And here below we have an interactive demonstration where we can slide out the rate of the event. We'll just slide this out a little bit and then have that change our plot here, and then we can go through and we can click and find new values and visualize how the probability function looks for the Poisson distribution. So that's just one example. You can see here there are lots more, and in fact we've actually put all of our math apps from inside of Maple. So inside of Maple we have just over 370 different math apps available. We've put all these into the Mobius cloud, so if you have a student who doesn't have Maple, they can go through the Mobius project website, they can view all the math apps here, or on our website we have a free download of our Maple Player, which is a free Maple reader for Maple documents. But it's not only a reader, it's also an interactive reader. So if you've got interactive content such as a Mobius app, you can interact with it directly with with the Maple player. So both of those are options if you have students or you have other peers who may not have a copy of Maple. These are both ways for you to share that content with them. And I'll close by making another reference to some more content we have available to you. So this is over on our YouTube channel. You'll actually find that we've just started up a new playlist for some tutorials that feature statistics with Maple. So right now we've got 11 or so videos in there, and we'll be adding many more in the coming weeks for statistics with Maple. So that's another good resource that'll actually broaden some of the examples that I've walked through today, as well as providing links back to those Mobius apps. So with that, I hope you've enjoyed today's webinar. Thank you very much.